Now let's work on a simple example. We will make a shallow truss formulation. So here again we say that our deformations are small and our displacements are small. So let's take a truss member like that, and the length of truss member is L. So I have a roller support here, and let's call this displacement. It's not a displacement, but this distance as equal to Z. So that will be the initial configuration. And here, this distance is L hat. And let's assume that I'm applying a force P. So due to that P, it will deform. Let's do it this way. Still I have a roller support here. I got P here, and this is the deformed configuration. So the length of that member is now equal to L prime. That's the rotation, theta. And I will see a normal force on this truss member. Okay? And let's say that the deformation that we observe, this truss is equal to W. So if I write the equilibrium equations at the deformed configuration, I'll have the following equation. P is equal to n times sine theta, right? So the vertical component of this n should be equal to P. That's the equilibrium condition. And instead of sine theta, I can just write sine theta as equal to, I got n, W plus Z divided by L double prime. Okay? Now, here we make an assumption, assuming that theta is small, then our equilibrium equation becomes equal to P is equal to n times W plus Z divided by the original length. So that's called as, this is our first equation. So here again we said small displacement. So here I use that assumption. So instead of using the final length, I use the original length. Okay? Now we say that we will be using the small deformation, so I'll say Let's use engineering strain definition. So we say that strain is equal to final length minus the original length divided by the original length. That's our engineering strain definition. So in that case, that will be equal to final length minus original length, L, divided by the original length. Okay? And if we write what final and the original lengths are, so the final length is equal to Z plus W squared plus L hat squared, that's the original length, sorry, final length, minus square root Z square plus L hat squared, again divided by Z squared plus L hat squared. That's our engineering strain. And if we simplify this, we end up with the following equation: 1 plus Z plus W divided by L hat square over 1 over 2 multiplied with 1 plus Z plus L hat squared minus 1 over 2 minus 1. Now we need to simplify this. So for that I'm using the Taylor series expansion. And ignore the higher order terms. You can just say that the strain will be then equal to 1 plus 1 over 2 Z plus W over L hat squared 1 minus 1 over 2 L hat squared minus 1. Then this will be equal to 1 minus 1 over 2 Z over L hat squared plus 1 over 2 Z plus W L hat square minus 1 over 4 Z plus W L hat square Z over L hat squared minus 1. And we can ignore this. And compared with the other terms, these ones will cancel. And at the end of today, our strain will be equal to Z over L hat W over L hat plus 1 over 2 W over L hat squared. Okay. Now to further simplify it, I'm assuming that the initial crookedness in that truss element is small. We say that L is equal to L hat. Then E will be equal to Z over L W over L plus 1 over 2 W over L squared. So that will be the strain definition. Okay. Now, for an elastic material, the axial force on the truss is equal to E times A multiplied by the strain. Then in that case that's equal to EA multiplied with Z over L, W over L, plus 1 over 2 W over L squared. Then our force displacement relationship will be as follows. P is equal to EA over L cubed. I got Z square W plus 3 over 2 Z W squared plus 1 over 2 W cubed. Okay. Now, in order to calculate the stiffness matrix, remember that stiffness matrix is actually the slope of the P delta curve. So we can say that the KT, now in that case will be the tangent stiffness, is equal to dP over dW. So if we use this expression and calculate the dP over dW, this will be equal to Z plus W over L dN over dW plus N over L. So what I did here is I take the derivative of this expression and I obtain the following. Now I know what dN is equal to. It's this expression. I can take the derivative with respect to W. And from there, I obtain my tangent stiffness matrix as follows. I got EA over L multiplied with Z over L squared plus EA over L 2 times Z times W plus W squared over L squared plus normal force divided by the length of the member. Now let's take a look at these expressions. That's the linear part. This is the linear stiffness matrix, because as you see, it doesn't have any terms related to the deformations or related to the axial force on the member. So if you make Z equal to 0, then we will have a straight truss, and the straight truss doesn't give us any deformation in the vertical, any stiffness in the vertical direction. So this term will be equal to 0, right? And if you make Z equal to L, Of course, this formulation won't work for that. We assume small deformation. We can just say that Z is equal to 0. Okay. So this part of the stiffness matrix is called the linear or small displacement stiffness. So that's the stiffness matrix we have been deriving by using the first order analysis approach, okay? So we are assuming small displacements, we are writing all our equilibrium equations for the undeformed configurations, and we were getting this part of the stiffness matrix. And this one involves terms belonging to the initial geometry. Now the second term, as you see, involves the terms with the deformations. Now the structure is in its deformed configuration. How does the stiffness change due to the deformations? Okay, so this part of the stiffness matrix is called the initial displacement stiffness. And it describes the change in the stiffness due to the nodal deformations. Okay. Now, of course, your structure deforms now that the effect of the internal forces change, and this part of the stiffness matrix is called geometric or initial stress stiffness. So basically, when we look at the tangent stiffness in a geometric nonlinear analysis, we see three terms. One of them is the elastic linear part, the part that doesn't involve any geometric nonlinearity. It's the you use the undeformed geometry and derive the stiffness coefficient. The second part of the stiffness matrix involves the effect of nodal displacements. Yeah, right? Your structure deformed, so you want to write your equilibrium equations for the undeformed geometry. How does your stiffness terms change? So that's that part. And we also have the effect of the internal stresses. It's your structure has internal stresses and it moved. Now, what is the effect of these internal stresses due to the deformations is described at this part of the stiffness matrix. Now let's take a look at the behavior of the shallow truss. Remember that that's our truss element. We have a roller support here and a pin support here. This distance that's equal to Z, and now I'm applying a force in the reverse direction, and I'm also adding a spring here to stabilize the system. Now, as a starting point, we will just work on this problem without any spring stiffness. Ks is equal to 0, and we assign the following values to the truss. Now we already derive this equation. That's the load deformation curve, equation for the load deformation curve. This is the expression for the axial force on the truss, and that's our tangent stiffness, equation for the tangent stiffness. Now, we said that the tangent stiffness has actually three stiffness matrices. One of them is the linear stiffness, it's this part. We have the stiffness due to the initial displacement, the effect of displacement, how does it affect your stiffness matrix, it's right here. And we also know that the initial stress or the geometric stiffness matrix equation is as follows. Now we will plot it for W equal to 0 to minus 100. That's the equation for it. And when you add this spring stiffness, we have an additional stiffness here. But as I said before, we will take Ks as equal to 0. Now this is the load deflection curve for that truss. Remember that, let me draw it one more time. So that's our truss element, no spring. And the load is in the downward direction. That's Z. So when W is equal to 0, we are at this point and we have the following initial stiffness, but as it moves in the downward direction, the stiffness decreases. So as W, I'm plotting W over Z. So at somewhere here, we reach a limit point. That's our limit point. And after that limit point, we see a dynamic takeoff. So as it moves down, somewhere here, due to the geometry, the structure doesn't create enough resistance in the vertical direction. So it becomes unstable and it dynamically takes off. So it moves, and then when go to the reverse direction, now the normal force becomes a tensile force, and because of this reason we see another limit point somewhere here, and the structure becomes stable and starts to carry the applied loading in tension. So as the angle increases, so as this angle increases, we see more resistance in the vertical direction as also shown here. That's the load deflection curve, and from the simple example, we see a snap-through behavior response. And between these 2 points, the structure is unstable, dynamically takes off. Now let's take a look at how the stiffness matrices change for this load deformation curve. So here in this graph, I'm plotting all the stiffness matrices. So the black one is the tangent stiffness. The red one is the linear stiffness. Of course, it doesn't depend on the deformation, it's constant. We have the initial displacement stiffness and the geometric stiffness. So we see the effect of the geometric stiffness as the structure moves, and as it deforms, the axial load increases, and depending on the axial load, we see such a variation in the geometric stiffness, and then the compressive force becomes a tensile force, and we get positive stiffness due to the internal forces in the truss element. Now this one is the geometric the initial displacement stiffness. So as it deforms, we see a negative behavior in the initial displacement. This means that when I write the equilibrium equation in the deformed configuration, if we forget about the geometric stiffness, due to the deformation, the stiffness of the system, of the structure, decreases. But of course, the total stiffness is the summation of all these three, and we see this black curve. Now, when we are at the limit point, so this is where we see the limit point, we see zero stiffness. Okay, at the limit point, the tangent stiffness is equal to 0. So at the other limit point, again, the tangent stiffness is equal to 0. And in between these 2 points, these 2 limit points, we see negative stiffness. So that's why the equilibrium is satisfied with we see a dynamic equilibrium. There's no static equilibrium because we have negative stiffness on the system, so it moves very fast, it buckles actually, and between these 2 points it moves, but as we reach to the second limit point, you can see we have a positive stiffness. We see some resistance in the system, and as it moves further, we got positive stiffness and we see the resistance. So if we want to solve or analyze this structure by using a numerical method, we should be able to catch the limit points, and we should be able to trace this unstable region and find out our final value. So this is the snap-through response, but I can add a spring to the system so that we will always have some stiffness in the system. This is Ks and that's P. So depending on the Ks value, we can see a stable system. So when Ks is equal to 0, we have an unstable system, a perfect snap-through. So I make Ks is equal to 1, then we see a better behavior, but some very low stiffness at this point. And when Ks is larger, we see always a positive slope. Of course, the tangent stiffness changes in these 2 points, so the slope decreases, and after a while, as the compressive force on the system becomes a tensile force and W is larger than Z, we see a stiffening behavior. So our solver also should be able to catch such a stiffening behavior. So our next task is to develop a nonlinear solution algorithm so that we can trace this load deformation curve fully, so that we can understand how the structure behaves under the given loading.